Gentlemen, may I have your attention, please? The show starts in 5, 4, 3, 2, 1, go.
Hello everyone. Today my group will present about metallic bonding and band theory. We from F4AS12055. This is our group members. First, Anis Khairunisa binti Azlin Khair. Next, Nurun Najwa binti Nur Azli. Next, Zalia Maisara binti Zaili. Next, Muhammad Aimin bin Abdurrahman. And lastly, Muhammad Farid Kamil bin Ashari.
The objective of this presentation are 4 main points. First, to explain the basic concept of metallic bondings. Second, to describe band theory in metals. Third, to relate both theories to the physical properties of metals. And finally, to discuss the real-life application of metals based on these theories.
Metals are elements that are widely used in daily life and modern technology. Common example of metal is copper, iron, and aluminium. These metals are known for several important properties such as high electrical conductivity, high thermal conductivity, skinny metal appearance, and the ability to be malleable and ductile. To understand why metals have these special properties, scientists study 2 important theories, which are metallic bonding and band theory.
Metallic bonding is defined as a force that holds metal atoms together in a metallic substance. Unlike ionic or covalent bonding, metallic bonding involves many atoms sharing electrons collectively rather than forming bonds between specific pairs of atoms. Metallic bonding occurs when metal atoms contribute their valence electrons to form a sea of delocalized electrons. These electrons are not fixed to any particular atom and are free to move throughout the metal structure. As a result, metal atoms become positive ions, or metal cations, which are arranged in a regular crystal lattice. The structure is stabilized by the strong electrostatic attraction between the positively charged metal cations and the negatively charged delocalized electrons. Metallic bonding is non-directional, meaning the bonding force acts equally in all directions. Because of this, metal atoms are able to slide past one another without breaking the metallic bonding. This characteristic explains why metals are malleable, meaning they can be hung into sheets, and ductile, meaning they can be drawn into wires.
Effects on metal properties. Metallic bonding explains several important properties of metals. Metals can conduct electricity because the delocalized electrons are free to move when an electric field is applied. They also conduct heat efficiently because these free electrons can transfer kinetic energy rapidly. In addition, the non-directional nature of metallic bonding allows metals to be malleable and ductile, making them useful in manufacturing and construction.
Next, we are going to talk about the band theory. Band theory explains the electronic structure of solids. When a large number of atoms comes together to form a solid, their atomic orbitals overlap and combine. This results in the formation of energy band rather than discrete energy levels, specifically the valence band and the conduction band, which may be separated by a band gap. In metals, the valence band and conduction band either overlap or have a negligible band gap. This means electrons can easily move from the valence band to the conduction band without requiring much energy. As a result, electrons can move freely throughout the metal, which explains why metals are excellent electrical conductors. Band theory also helps predict other properties such as thermal conductivity and electrical behavior.
This slide shows the comparison of band structure between metals, semiconductors, and insulator. In metals, there is no significant band gap that allowing the electron to flow freely. However, in semiconductors, there is a small band gap, while in insulator, the band gap is quite large, causing the preventing of electron movement. This comparison helps us understand why metals conduct electricity better than the other materials.
It's Professor Dave. Let's learn about conductivity and semiconductors.
He knows a lot about the science stuff. Professor Dave explains.
Much of our technology relies on substances that can conduct electricity, meaning that they allow the flow of an electrical current. But what is it about a material that allows it to do this? Conversely, if insulators are things that do not conduct electricity, why is that the case? And finally, what are semiconductors and where do they fit in? Let's learn about all of these terms now. So as we said, conductors conduct electricity and insulators do not, while semiconductors are materials that have a conductivity in between that of a conductor and an insulator. Because of this intermediate conductivity, semiconductors can be controlled and used for technological purposes. The explanation for the conductivity of these substances requires that we take a look at molecular orbitals in metals and network solids. So if you need to review this concept, check out my tutorials on molecular orbital theory first. Otherwise, in order to put things into perspective, we must understand that these materials are not small molecules comprised of a handful of atoms. These are huge arrays of a particular atom or repeating formula unit, stretching endlessly in every direction. We know that when two atomic orbitals combine, two molecular orbitals will be generated, one lower energy bonding orbital and one higher energy antibonding orbital. Thus, as more and more covalent bonds form, more molecular orbitals will be generated to house all of these electrons. Here we can see the molecular orbitals involved as many atoms come together to make a network solid that will be a conductor. As the number of atoms increases from 1 to 2 to 4 to a number so large that it can be compared with infinity for practical purposes, the number of orbitals will increase in the same way. And as the number of orbitals becomes incredibly large, they will begin to resemble one continuous band. There are some important things to note about this model, which we call band theory. First, the atoms are held together by electrons in the lower energy bonding orbitals, as these are filled first, while the higher energy antibonding orbitals remain vacant. Second, in a conductor, the difference in energy between the highest occupied molecular orbital and the lowest unoccupied molecular orbital is infinitesimally small, which means that electrons can move freely between orbitals, and this is the key feature of a conductor that allows it to conduct electricity. Comparing substances with differing conductivities, we will notice something called a band gap, which is a gap in energy between the bonding orbitals, or valence band, and the antibonding orbitals, or conduction band, named as such because electrons must access these orbitals in order for the substance to conduct electricity. Conductors, as we said, have no band gap, or just a tiny one, so electrons can flow easily. Insulators have large band gaps, which does not allow for a current to form. Semiconductors, on the other hand, have a small enough band gap that thermal energy in the system is able to keep some of the bonding orbitals in the valence band empty and promote some electrons into the antibonding orbitals in the conduction band. This is why semiconductors conduct electricity better at higher temperatures, because there is more thermal energy available to promote electrons into the conduction band, and thus a stronger current is able to form. So what kinds of materials can act as semiconductors? Here are some common substances along with their respective band gaps in electron volts, so we can get a sense of the range that is permissible. We will notice that some of these substances are elements, like silicon and germanium, and some are compounds, like lead sulfide. Once the band gap becomes sufficiently large, a substance will become an insulator, like diamond or aluminum nitride. Apart from temperature, another way to increase the conductivity of a semiconductor is through a method called doping, which is where impurities are mixed into a substance, and this impurity can either have more or fewer valence electrons than the substance. If the impurity or dopant has more valence electrons, the conduction band will begin to fill and current can flow. This is called an N-type semiconductor, where N stands for negative. If the dopant has fewer electrons, the valence band will end up not completely full, and current will again be able to flow. This is called a P-type semiconductor, where P stands for positive. Electronic components like diodes and transistors utilize both P and N-type semiconductors, so these techniques are very important indeed. We will dive into these kinds of materials in more detail in a future engineering course, but for now, let's move forward and learn more chemistry. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
The concept of metallic bonding and band theory are applied widely in real life. For example, copper is used in electrical wiring due to its high electrical conductivity. Aluminium is used in power cable because it is lightweight and conduct electricity efficiently. Iron and steel are commonly used in construction because metallic bonding provides strength and durability. Band theory is also important in electronics, where metals are used in circuits and also electronics to conduct electricity.
In conclusion, metallic bonding explains the structure of metals and the presence of delocalized electrons. Band theory explains the energy levels of electrons in metal and their ability to conduct electricity. Together, these theories help us understand the physical properties and technological application of metals in everyday life.
This is our references. Thank you for watching our video. Any question, you can ask in comment section below. Bye!